Thank you for coming. Today, I'm going to talk about my exciting research and interesting story with you. Let's get started. We are building the robot and we made it faster and dynamic and agile because we want to make this robot to save a human's life and help the human's life by making this robot is more productive and safe to safely operate near humans. And it's difficult. It is actually really difficult, and there are various reasons for it. But I can summarize it by three categories. One is the modeling. Physical system is impossible to exactly know. We never know the exact mass, link length, central mass, inertia. So modeling is always has some amount of the uncertainty. And second thing is the sensing. We can never know where the robot is exactly and the velocity of the system. But even though we have everything, we don't have the actuator. Ideal actuator can generate the force amount, exact amount of the force at the right time and the right moment. This kind of the limitation, this uncertainty level are different, but cannot remove completely. So we have to play with it and live with it. Our research goal is creating high-performance legged robot by addressing this fundamental constraint of robot hardware and controller. It is important to say hardware and controller at the same time. And let me introduce one interesting story. Okay, if we do not address the hardware and controller very well, then we're going to see this kind of humanoid robot, disaster response humanoid robot. By the way, I don't have any personal opinion about this robot. This robot got third prize in this challenge, and I like this team. But see the speed of this robot. I want to give you some time to carefully watch and truly feel that what is the speed of the current state-of-art humanoid robot. It's not fast at all. It's hard to believe that this robot can save our life when there is the bomb, explodes, earthquake. So disaster response robot is still too slow. And I think it is because they rely too much on the anchor actuation and flat feet. Because when you see the actual manipulator robot in the factory, they are really fast. As soon as we put that arm on top of the leg, then it starts to be slow. So locomotion is a problem. Okay, let's remove both. And this is the system we come up with. If we don't have any ankle or foot, and then still succeeded to make this robot balanced, then we can say that we accomplished the truly dynamic balance, dynamic bipedal locomotion, and speed up every humanoid bipedal locomotion. That was the idea. Because this system is quite unique, there are not much algorithm I can use, so I designed it from scratch. So design the planner, I'm going to explain later, and tested it in the simulation. And it worked. It actually worked well, stepping over the 7-centimeter obstacle and stepping down from it, but still it balanced in dynamic simulation. Okay, we're so excited because once we implement this algorithm in real robot, then we're going to be the first teams to succeed to make a bipedal locomotion without anchor actuation. And this is the experimental result. After couple of months. Okay, yeah, now you can see the three challenges. In simulation, we exactly know where the robot is, exact model, we have an actuator, ideal actuator. But in physical world, we need to handle these three challenges all together. It is difficult. And how difficult it is, this shows the more result. This is 100 failures, all ends up similar result. By the way, this experiment happened in the one day. So I literally did this since more than 6 months. So it is really exhaustive process. What is the issue? the question really bothers me is that we actually succeeded in the simulation. What's the issue? Let's go back to the planner. So this is our planner's idea. Every steps, we are sending the center of mass position and velocity to the computer. And even though this entire robot dynamics is complicated, if you pick the center of mass and stance put as the core point, focusing on these two dynamics, then it's similar to the inverted pendulum dynamics, which means that we can easily predict what is the center of mass position and velocity when switching is happened, when it landing the next location. Okay, the question is, what is the proper landing location? I decide the landing location to make the center of mass velocity becomes 0 around the middle of the swing time. Then we can guarantee the swing time, and the center of mass is going to change the velocity every steps, which means that this center of mass is oscillating around the center and then stay inside of in between the landing location, these 2 foot. So if we can constrain the motion in between between these 2 steps, the robot cannot fall down. It won't fail. Then the idea is simple. If we know the center of mass state, position, and velocity, and if we can control the full landing location well, then this robot must not fall down. This is the center of mass velocity profile we got from the robot. And if it is following the inverted pendulum dynamics, the velocity profile should be like this, goes up, down, and goes up, down, and up, down. But as you can see, this signal is complete noise. So center of mass velocity profile tell me that, okay, you need to work harder to get the better center of mass velocity. But more fundamental question we have to ask is what is the sufficiently small estimation error and control error? To answer the question, we need some mathematics. And after analysis, we come up with this result. Okay, if there is no limitation, there is no kinematics or the noise limitation, then whatever this state, wherever the robot starts, it goes to converts to the origin, converted to the 0 velocity. So controller can stabilize the system if there is no limitation. But robot has a limitation, kinematic limitation. In this case, in case of this biped, step location limitation is about the 40 centimeter. So you cannot take a longer than 40 centimeter step. Because of it, we cannot cover the entire state space. Only the state around this blue region, inside of the blue region, is a feasible state. And if there is the error in the landing location control, and if there is some error, uncertainty in the center of mass state estimation, then we cannot guarantee the certain amount of stability of this amount of the state. So if landing location error is about the 4 centimeter, and then we can make the error in the center of mass state estimation 3 centimeter, then this orange ball is an uncertain region, which means that we cannot guarantee the stability of this system in this state. What does that mean? That means that almost all feasible state is not guaranteed to be stable. So if we want to make all the feasible state is stable, which means that we want to shrink down this ball into this region, then we need to make the center of mass estimation error below the 2 millimeter and the landing location error below the 1.5 centimeter. So the system should be a lot more accurate. That was the conclusion of this analysis. So going back to the control architecture, this is the original control architecture. You don't need to worry about all the details. The important thing is that we revise this controller to accomplish this amount of the accuracy. and then updating upgraded the hardware and then changed the sensors. And we got this result in the end. So I think I spent 6 minutes to explain this entire research, but it actually takes 6 years. So this is a 6-year research. It takes a lot of times, but we can claim that this is the first dynamic balance of the passive anchor biped robot using full body dynamics-based controller. And the important lessons we got from this project is that we need to understand hardware limitation and control software limitation at the same time, simultaneously consider the whole entire system. Okay, great. Can I use this controller for other system by combining the other controller? Sure. This is the Minichira Locomotion demonstration with their original controller. This controller used the simplified dynamics. It is okay, but if we speed up, then it fails. Once we integrate our full body dynamics controller with this original controller, then this is the locomotion speed we can reach. I hope the video is not very choppy. The speed of this robot is 3.7 meters per second, one of the fastest legged robot in the world. It was took in 2 years ago, but still the top speed. I'm proud of it. So 3.7 meters per second is limited by the hardware capability. We hit all the joint limit and torque and the power limit, but that means that our controller can make the even higher speed if we upgrade the hardware. Anyway, can we use this algorithm to do some more interesting behavior, but in completely different system, like a humanoid? This is a bunch of jump demonstration. Jumping part is done by the trajectory optimization, but landing control is similar to the locomotion controller I used in the miniature running. So far, it's all about the blind walking and the jumping. So there is a big assumption. Terrain is going to be flat and it's not going to be very slippery. But if we want to do more than that, like a really rough terrain, then we need some type of the camera. This robot currently watching this environment and building up the map. And you can see that how this robot understands this environment up and down. And it categorized that, okay, blue is not a proper place to stepping up, and green is a good place. If it takes too high obstacles to be stepping over, then you can use that its dynamic behavior, the jump. There is no autonomy. I actually pushed the button to make this robot jump. That autonomous part is something we're currently working on. And we also developing the other type of the controller, which can be used for the various situations. One of the critical limitation of the model-based controller is that whenever we meet the new situation, we need to develop a new controller and new formulation. So that's not scalable idea. We are starting to look into the data-driven algorithm and integrating the reinforcement running in the robot control, which is more scalable ideas to make this robot practical and useful in various situations. Of course, this is not unique approach. But what unique part is that we really want to make this system, this controller can stabilize a dynamic system like this humanoid, this biped robot. We custom designed all this robot and built the robot. This robot, of course, doesn't have a foot or ankle, and we'll see the reinforcement running plus our controller can stabilize these systems. We are still working on it. Okay, let me summarize the talk. Our vision is to develop the dynamic legged robots for common goods. So we are currently developing guide dog robots. In this development, we continuously contact and interview with blind people who actually use the guide dog robot and guide dog trainer to get the feedback for our technology. And this is the pictures the part of our interview. And we are developing the exoskeleton because we are really uncomfortable as a robotics researchers to see that the people still bothers and then getting difficulty because of the disability, their life logistics, and people still face the dangerous situation. But we wanna help them and reduce this difficulty. And life logistics is also one big chunk of this, hassle. This is the imaginary pictures. It's one of the vision we have using the multiple legged robot, humanoid robot, collaborating to carrying the big object, heavy object. And to do that, we have to build the hardware and software together. This is the preliminary design of our biped and the exoskeleton robots we are building here. In our lab, we are building the hardware and then software together. Okay, that's pretty much what I prepared today. I'm happy to answer any questions you have any. Thank you.
I can have a quick question. So, Professor Kim, have any of your students started using RL in the real robotics setting? Like, have they?
Yeah, so of course, and we tested a couple of the RL algorithm recently published from the KAIST. We tested in the Minichira and worked greatly. So far, we don't have our own algorithm because we just started. But yeah, we tested it and it worked. Some of them work, some of them not work. Yeah,
do you do any kind of trick to make RL work, like domain randomization or something like that?
Yeah, we tried a couple of things. Of course, domain randomization is one of it. We're thinking more about how to utilize our low-level controller and then reduce the dimension and then decrease the gap between the simulation and controller, because our controller guaranteed some amount of the robustness. So it can, make this sim-to-real processes smoother.
Thank you. Yeah.
Yeah. Thanks for question.
Maybe another question. So, are you using RL for pure end-to-end training, or like you use RL in like some middle part, like what's the action space? Is it like just the joint torque or joint velocity for the robot?
For now, we're thinking the input is going to be state, including the terrain. Output is the joint position. But we are thinking more about how to make this things more, midpoint training. Like output of the neural network is central mass velocity command, something like that.
Yeah, gotcha.
Yeah, as you know, that we cannot say that okay, this is the picture, and then figuring out how to walk over the terrain.
Yeah, that's gonna be too difficult, I think. Yeah,
that's
it's better to have some
great approach, I think.
Right, I agree.
Any other questions? How many of you know the Boston Dynamics?
Yeah, I'm closely following their work. Yeah, very interesting to me.
Okay, yeah. If you know the Boston Dynamics, and the easiest way to understand our lab's philosophy is that we want to compete against the Boston Dynamics.
I had a question. So, initially you spoke about you wanted to remove basically the flat foot. So you want to remove the ankle actuation, right? And therefore you wanted to get rid of the robot having a flat foot. But when I intuitively, if you think about the fact that even as a human, balancing on your tiptoes is a lot more difficult than just balancing on your regular 2 feet. So I was wondering, so I got the motivation, but were there any other options? Just because it seems like a very challenging problem from the beginning, especially to have just 2 feet and then flat surface.
Okay. Yeah. First of all, we do not try to remove this foot and ankle. We try to find a way to stabilize the system, even though there is no ankle in the foot, because we don't want to rely on it. That was the reason of this. There is the motivation of this project. Of course, once we made a humanoid robot, then we are going to put the foot and ankle. That is the only way to make this system is aesthetically stable. But we want to find the answer for this question. Is it possible to make this robot stable even without ankle or foot, ankle actuation or foot? As you pointed out, it is important to have an ankle and foot, and then that is how the people use their body. And we want to imitate. We are going to build the final humanoid robot. That is one of the big things should be happens in the lab. Custom design the humanoid robot, and in that robot we're going to put the 2 degrees of freedom ankle, and then this amount of human shaped foot. Does this answer your question?
Yeah. Thanks.